So now we want to see how we can actually solve the alignment problem. So given that we have a scoring function and we assume that's stable and we know what it is, can we actually find an optimal alignment? Now you already saw for the simple problem here that by eye it's quite easy to spot this alignment. But if the sequences become longer, this problem becomes much more difficult. And you can imagine that if you think about typical protein sizes of about 200, 300 amino acids, it is quite difficult to spot by eye the optimal alignment problem. And so we really need to solve this problem computationally. Now, luckily, there's quite an efficient algorithm for calculating the optimal sequence alignment score. So first we'll try and look at the method and what comes in and what comes out. And here we start with thinking about global pairwise sequence alignment. Later we will also see local pairwise sequence alignment. But for now we assume that we want to match the entire sequences, which means the global part. So for the algorithm as an input we typically have two sequences, DNA or protein. We have a substitution matrix, or at least a scoring scheme for the matches and the mismatches, and we have gap penalties. Now, given these parameters, the algorithm tries to find the optimal alignment between the two sequences. Then, what you get as an output is indeed an optimal alignment, and also an associated optimal alignment score. So you actually get two things. Sometimes you also get a significant score out of these types of methods. Now, if we look at this in practice, this will be a typical output for an amino acid alignment. So here you have query subject. You actually see that the sequence is long. So we have 187 amino acids for the first sequence and 194 for the second amino acid here. So you see it runs along the lines. And you see here indicated between the two sequences the matches. So you see only occasionally the sequences actually really match. Nevertheless, if you look at this alignment, you see actually the matching is relatively good. You see few gaps. You see actually quite a lot of similarities. So this is actually quite a nice alignment between the two sequences. You also see that the score is given here. Now, the question now is how do we actually get to such an alignment? Now, luckily there's a very nice algorithm, the Needleman-Wunsch algorithm, that can find this optimal global alignment. So what we consider in a little bit is an alignment matrix, and how that works we will see it soon. We take two sequences, we have our scoring parameters here. In this case we consider DNA, we consider a simple scoring scheme with 1 for a mismatch, minus 1 for a match, minus 1 for a mismatch, and a gap penalty of 2. And here is the scoring function for the algorithm. And what you actually see is here these are cells of a matrix, we'll see it before. We can actually calculate the next cell in the matrix based on looking back at previous cells in the matrix and then adding either the matching score from here, so the Sij, or subtracting the gap penalty in these two cases here. So now we'll actually look at one of these matrices that we will fill in. Now this is a typical global alignment matrix, and you see here that you have the positions of the first here and the second sequence here along the axes, and now each cell here is one of these Hij cells. So we say this is cell H00, so it's the cell H with coordinate 0, 0. Now if we move along one to this side here, we get into the cell H01. So we've moved up 1. Now if we want to calculate this score, we actually have introduced a gap, because going in this direction actually means we match this symbol here, G, with a gap here. So if we do this here, we actually have to use this here, and we come from 0, so we actually get a minus 2. So one of the first things we can do, because we of course always come from a 0 score when you haven't aligned anything yet, we can actually start filling this in. So here you get -2, -4, -6, and so on. So if we fill this in, we can initialize the matrix like this with the gap penalties. And this is already actually filling in these H scores here for going into this direction. So J -1, so we're looking back. So for this -4 here, you looked at this one here, and you took this one. And so you go on. Now we can start with filling in the first matrix cell. And we also always start at the top left and then move slowly to the bottom right. Now here it becomes more interesting when we want to start filling in this cell, because now we have to look at all these 3 cells. We have to look at this cell, and at this cell, and we have to see what gives us the maximum score. So if we come from this cell here, we need to consider 0, so that is the H here, Hi -1, J -1 is this cell, and we need to match the score. Well, here we have G and G, so it's actually a match. So we'd end up with a score of 1. But we also need to consider the other 2 possibilities. So you may actually come from here or from here. In this case, we assume that it's not matched, and so we introduce a gap. But we do need to consider the previous score and add a gap penalty. So in both cases, this would be -4. So then in this case, we'd have a -4, here we have a -4, and here we have a 1. So in this case, 1 is the maximum, and that's actually the score we fill into this cell here. So if we apply this, we can keep going, and it's very important that you actually track which of the directions you took when you make this decision. We can also fill this in a separate matrix, but here with red arrows it's indicated from which cell, so which choice here in the maximum was actually made on the decision to put a 1 here. This is also called the backtrace matrix. So you have a secondary matrix here that remembers which path we took along. And we'll need this later to find the alignment back. Now here again, we'll consider all 3. We'll take the optimal score, so the highest score, and it turns out actually introducing a gap here is more advantageous than going over the diagonal here and introducing a mismatch of A and G. And so we can go forward and fill in the entire matrix. Now here you see the entire matrix filled in, but what we wanted to get out is a score, the optimal score, and we wanted to get out a sequence alignment. Now the optimal score is actually easy in this step of global alignment. It's simply the score in the right hand bottom corner. So it's the final diagonal element here, the large match here. Now finding back the alignment, in this case we really need the backtrace algorithm. So this is why we needed to draw in the arrows and remember where we came from. So we need to actually see how we got here. Now here the backtraces are gone, and now you actually can see that we have multiple paths possible for the alignment. So we can draw this out. We have here the first, there's of course nothing, and then we have a G and G matching. We have an A and an A matching, but now we have 2 possibilities. We can either first introduce a gap on this sequence here, and then later match this G with this G once we're here. We can also decide to make a mismatch, a match between the G and the G here, and then later introduce a gap here. So if we look at that, these are the possibilities. So we see here a middle road, a high road, and a low road for the sequence possibility. So if we look at the 2 possibilities here, aligning the A and the A, in this case introducing the gap already after the first A, that would be corresponding to this alignment here. In the other 2 alignments, we see that the gap is made at a later position, and so the drop over the introducing the gap in this sequence here, for this sequence here, is actually done at a later stage. And so you see actually that there's 3 alignments in that case that all score 2, and they're actually, 3 of them, all the optimal alignments, and they're all solutions to the problem.